Hello, my dears. How are we doing? Well, I'm just fantastic. Thank you so much for asking. Welcome back to our second flipped class of Unit 1. So last time we were together, we chatted a little bit about how to solve some slightly more complex equations that we lovingly dubbed multi-step equations. And we saw how the tools that we dusted off at the end of Unit 0 could be used to help us break down these equations with a couple more moving parts. Well, since we're in the business of solving equations, and we're gonna be in that business for a while, our question should be, well, how can I solve any equation, no matter how simple, no matter how scary, no matter how complex? So for today, let's continue our journey down this same road. We're gonna up the ante a tiny bit, and we're gonna see how we can once again take the tools that we've encountered and use them to make sense of some even more complicated multi-step equations. So, we're in multi-step equations, part 2, our second class of Unit 1, however you choose to title your notes. And we want to look at equations like the one in front of us. So take this, friend. 2/3 minus x squared, x over 2, equals 5 over 6. So I have two questions for you. First of all, how is this problem different from what you've encountered before? So let's stop and answer that first. How is this different from the problems that we've seen up until this point? Take 10 seconds. What do you think? Go. Well, if you're like me, I see 2/3, 5, 6, x over 2. Those are fractions. Up until this point, I've gotten really good working with whole numbers, and I'm okay with fractions, but whole numbers feel a lot safer, a lot easier to work with, a little bit less complicated. So if I'm thinking strategically, my goal here should be, well, maybe I don't like the fractions. As a mathematician, you have a superpower. And that superpower, whether you realize it or not, is the ability to take problems that you don't quite like the look of and change them into something that you do. In other words, as a mathematician, my power is the ability to take problems and make them look the way I want them to look. So my second question for you is, if I know that getting rid of the fractions is the way that I want this to look, something with no denominators, strategically, is there a choice that I could make that could get rid of all of these denominators, hopefully in as little moves as possible? So what do you think? Take 20 seconds. What might I do to get rid of these denominators? Okay, well, either way, hopefully you've done some percolating. We know that our goal here is to get rid of our fractions. I'm fine with them, but it's much easier for me if I can just work with whole numbers. So much like history, in math, often looking at where we came from can be really helpful in helping us determine where we want to go. So let's take a slightly simpler version of this problem and see if we can use it to motivate a choice that we could make to solve this friend. So let's look at this problem, slightly simpler. X over 14 equals 3 over 7. What's this guy an example of? It's a really prime case for a type of equation that mathematicians have developed, in fact, a cheat code for being able to solve. What's this called? 5 seconds, go. 4, 3, 2, 1. Level up, level up, level up, level up. This is an example of a proportion. Very good. So a proportion is just an example of a fraction equal to a fraction. But the thing about those fractions, because they're equal, that means the ratio of the numerators and denominators should be the same. So x to 14 should be the same ratio as 3 to 7. My goal here is to figure out what x is. So just like any equation, again, my goal is to do what with this? What am I trying to do here? You tell me. What am I trying to do? And what does it mean again? Same question that I asked back in last class. What am I trying to do with this and what does it mean? Go. 10 seconds. Well, it's an equation. And because it's an equation, that means I want to solve it. That means I want to find the value of the variable that makes it true. And well, how do I do that? I want to get the variable by itself. A proportion has a cheat code. What's the cheat code for solving proportions? Remind me. Well, given a proportion, I always have the ability to cross multiply. So if I take the numerator and the denominator of opposite fractions and multiply them together, so I take 7 times x and 14 times 3, this should give me a setup where it's much easier to get this value x by itself. A simpler way to write this, of course, 7 times x, well, let's rewrite that as 7x. 14 times 3, feel free to fact check me, I believe is 42. And now I'm in familiar territory. So ask yourself a question. 7x equals 42. Ask yourself a question about how you're going to solve this. Go ahead. Cool. Well, if you're like me, the question that I would probably ask, well, 7x equals 42. I want x by itself. What's in the way? And how am I going to undo it? So 7 is in the way of x being by itself. How is it connected to x again? Very nice, invisible person. It's connected by multiplication. So to undo multiplication by 7, I should probably divide by 7. So I'll take both sides of my equation and divide by 7. On the left, 7 and 7, they undo each other. And on the right, 42 divided by 7, well, that means that x should be equal to 7 times, well, 7 times what is 42? You tell me. 7 times. I don't actually remember. It's 7 times 6, right? 7 times 6 is 42? Yeah. Okay, so in this case, x equals 6. So cross-multiplying is always a powerful strategy when I'm working with proportions. Let's do 2 more really quick just to make sure that we've got that skill locked down. So 4/3 equals w over 18. N minus 8 over 25 equals 3/5. Let's solve for w, solve for n, find the values of the variable that make each of these proportions true. Give yourself 2 minutes, set a timer, see how far you get, and then we'll come back. All right, let's do it. Okay, so 4/3 equals w over 18. Again, my strategy when working with proportions is often to cross multiply. So here, if I multiply across, I've got 3 times w, and then 4 times 18, 4 times 18, I believe 4 times 8, well, that's 32, and then 4 times 1 is 4, carry the 3, that's 72. And then again, I'm home free. 3w equals 72. I want to get 3 away from the w. It's connected by multiplication. Let's use division to undo it. 3 over 3, these guys go away. And w equals 72 divided by 3, which is 24. And we can do the same thing with this n minus 8 over 25. It's slightly different. I mean, quickly, how is it different? Take 5 seconds. What do you notice? Well, I've got an n minus 8 as opposed to just a variable. So when I'm doing my cross multiplication, I might want to choose a way strategically to write that n minus 8 to make sure that all of it gets multiplied by the 5. What could you do to make it obvious that the entire n minus 8 is getting multiplied by that 5 there? Take 5 seconds, go. 5, 4, 3, 2, 1. Well, if the whole n minus 8 is getting multiplied, one way to indicate that it's, a unit is using parentheses. So I've got 5 times the whole quantity n minus 8, and then 25 times 3, well, that's 75. And from here, remember I've got 2 options. What are your 2 choices here to solve for n? Take 10 seconds. What do you think? Well, I've got 2 choices. This 5, I could distribute it, but remember we saw last class a slightly more efficient method that makes our lives slightly easier. I could divide by the 5 instead of multiplying it out and just get rid of it without needing to retrace my steps. So here, dividing both sides by 5 gets rid of the 5 on the left side. I'm left with n minus 8. And then 75 divided by 5, feel free to fact check me here, I believe is 15. oops, n minus 8 is 15, but I'm not quite done because n's not by itself. I need to get this n isolated. I have a minus 8. Let's undo it with a positive 8. And here n is going to be equal to 15 plus 8, which is 23. Very nice. So I'm cross-multiplying. But what's actually happening here? Well, let's take this example from above. 4/3 equals w over 18. What's another way to think about getting the w by itself? Well, if I take this w, another way to think about this, I could multiply both sides by 18. Multiplying both sides by 18 is really powerful for a couple of reasons. Number one, right, 18 and 18, multiplication and division, they undo each other. And I'm just left with w. And on the other side, I have 4/3 times 18. Well, 4/3 is a fraction. But 4/3 really means 4 divided by 3. So I have 4 divided by 3, and then I'm multiplying by 18. So this 18 is multiplication, this 3 is division. I could take this 18 and divide it by that 3, just like a fraction. If I really want to, I could write this as something over 1. 18 over 1 times 4 over 3. I could cancel out my common factor of 3. How many times does 3 go into 18? Well, that's 6. But it's really just like dividing the 18 by 3 to get 6. So I have now a 6 times a 4, which is a 24. Would you look at that? I'm right where I left off. So cross-multiplying, in a weird way, is actually a different version of this. What is 18 here? Look at the 18 and the 3. In the context of the problem, what do you think this is? So 18 and 3. I have two denominators, 3 and 18. 18 gets rid of both of them. 18 here is in fact a multiple of both 3 and 18, and here it's not just any multiple. It's the least common multiple, which makes 18 the least common denominator. So when I'm cross-multiplying, what I'm really doing is multiplying by the least common denominator. So if I look above, again, the idea here is that I can't cross-multiply, but cross-multiplying really just means something else. What choice could I make here? What number could I multiply everything by to get rid of every single denominator in one move? Take 10 seconds. What number could I use to get rid of every denominator here in one fell swoop? Go. What do you think? Alrighty. Well, if you're like me, I see a 3, I see a 2, I see a 6. The least common denominator between all of these is 6. A 6 will get rid of a 6, but 3 and 2 are both factors of 6. So multiplying everything here by 6 will make my life real easy. I'll get rid of all those denominators in one move. So my strategy here is to multiply by the least common denominator. Of course, it doesn't have to be the least. It could be any of them. But the least common gives us the smallest numbers and the nicest numbers to work with. So here, same idea. I'm going to take this and rewrite it just so that it's all in one place. So I have 6 times 2/3 minus 6 times x over 2, and that's equal to 6 times 5/6. And again here, if I really wanted to, I could write all of these 6's over 1. However, I can also just think of this over 3, for example, as dividing by 3. So I've got a 6 being multiplied, and I'm dividing by 3. Well, 6 divided by 3 is 2. Same thing here, I've got a 6 and a division by 2. Well, 6 divided by 2, that's 3. And then here, 6 divided by 6 is 1. And now I've got some nice parentheses. All that is multiplication. So I've got 2 parentheses 2. Well, that's 2 times 2 is 4. I've got minus 3 times x. Well, that's negative 3x. And I've got 1 times 5. There's 5. All I've got to do is get x by itself. Take a minute, pause. If you haven't already, find that value of x, and then we'll come back together and chat. Okay, 4 minus 3x equals 5. I want to get x by itself. Reverse order of operations is usually my MO. So here, I'll start by getting rid of the 4. Negative 3x is going to be equal to 5 minus 4, which is 1. Our 4 and our negative 4, of course, undo each other. And if I want to get x by itself, my last move here, I've got negative 3 attached by multiplication. Let's divide both sides by negative 3. X equals negative 1/3. Cool. If you don't believe me, check. Take that negative 1/3, plug it right back in for x. You should find that it does indeed make this equation true. Okay, one more for the road. Let's do one last one together, and then we'll talk a little bit more in class tomorrow. So a over 2 plus a over 3 equals negative 10. Again, think of what your strategy is going to be. Think about what choice you're going to make this look the way you want it to look. 10 seconds, game plan, go. Okay, you've got a game plan. What number do I want to multiply everything here by to get rid of both a 2 and a 3 in the denominator? Well, my least common denominator here, and the number I'm going to multiply each of my terms by, is 6. If you've got it, give yourself a 2-minute timer. Let's see if you can find, using this strategy, the value of a that will make this equation true. Pause the video, take 2 minutes, let's do it. And we're back. So I want to multiply everything by 6. A over 2 times 6. Again, I could go through the hassle of rewriting it, but I'll just leave it here for the sake of efficiency. I'm multiplying by 6 and dividing by 2. Well, that's the same as multiplying by 3. Over here, a over 3, I'm dividing by 3 and then multiplying by 6. Well, 6 divided by 3, there's 2. And then I've got negative 10 times 6. Negative 10 times 6 is indeed 60, except it's negative 60. So I've got a 3 times an a plus a 2 times an a equal to negative 60. And then from here, 3a plus 2a. Again, I want just one copy of a, but I see 2. So if I combine my like terms, 3a plus 2a gives me 5 a's in total. That's equal to negative 60. Last thing I need to do between me and freedom, I've got a 5a. I want just an a. Get rid of our multiplication by 5 using division by 5. And a is equal to negative 60 divided by 5, which equals negative 12.